Hey guys, so I would like to take a few minutes to talk through conservation of energy with you. Okay, if you're following along in the notes packet, I'm actually going to take out a couple of the demos because I think that we've done a lot with conservation of energy already. There's just some things that I want to make sure that we're clear on as we go in, because when we start talking about different theme park rides, we've done some ones that are kind of going in circles already, but when we start to look at drop rides and roller coasters and things like that, conservation of energy is going to be really, really important. And it'll be important for us to be able to recognize and identify when energy is being conserved and when it's not. All right. So that's what we're going to look at right now. We're going to skip over in the notes packet. There's a demo with the air track. We're going to skip over that for now. We're going to look at the ball drop, which we've done this before. We actually talked about Chewbacca and his energy. We're not going to look at the energy of the ball. We're just going to look at the energy of the ball Earth system. The reason for that is because when we look at the energy of the ball Earth system, then any forces between the ball and the Earth, namely the force of gravity, is going to be an internal force. Because in our equation, remember our equation for conservation of energy? So the initial kinetic energy, initial gravitational potential energy, initial elastic potential energy, plus any work, any energy being added in, remember work is energy coming in or out, must be equal to the final kinetic energy plus the gravitational final potential energy plus the final elastic potential energy. So whatever we start with must be equal to what we end with plus whatever we end up adding in. So when we look at the ball, we're looking at the ball Earth system so that we can have this internal gravitational potential energy. So if I ignore air resistance, I'm going to start with my ball up here about 2 meters off the ground. It's a little bit taller than me. So if I start at this point and I drop it, you'll see that it bounces back up. Now, first things first, when is energy being conserved? Well, energy is conserved if there are no non-conservative forces. Now, what are non-conservative forces? Well, non-conservative forces are forces that are external to the system. Non-conservative forces can be internal to the system as well if they're not accounted for in one of our potential energy equations. So if it's not an elastic force and it's not a gravitational force, then it's probably going to be a non-conservative force, a force that's either adding energy in or taking energy out. Okay. Now, in this situation where I'm dropping the ball, what are the forces acting on the ball as it falls? Well, as it falls, the only force, hopefully, that you've got is the force of gravity. Now, the force of gravity, as long as we're looking at the ball Earth system, the force of gravity is internal, and we would consider it to be what we call a conservative force. So from the moment that I release it until right before it hits the ground, energy should be conserved because all forces are what we call conservative forces. Now, the instant that it hits the ground, something new is happening, right? So once it hits the ground, so this is as it falls, and this is as it hits the ground. So as it hits the ground, something new is happening. We still have that same force of gravity pulling down as before, but now we also have the normal force of the ground pushing up. Now, I know that it doesn't keep falling. In fact, it stops falling and starts going up, which means that my normal force needs to be greater than the force of gravity. This normal force is what is called a non-conservative force. We can't account for it in our energy equation. There's no potential energy of the normal. And so that's what's considered a non-conservative force, a force that is outside, so it's not the gravitational force, and that is going to then cause a change in the energy of our object. And sure enough, you'll notice that when we drop it, if I drop it from here, when it bounces up, it doesn't bounce as high as where I started it from. Why? Well, as it falls, the energy is conserved, right? As we look at the top point and right before it hits the ground, we know that it doesn't start with kinetic energy. It starts with gravitational. There's no elastic potential energy. And there's no outside energy, so there's no work being done. Right before it hits the ground, it's got a lot of kinetic energy. No more gravitational because my height is now 0. And of course, no elastic. And so as it falls, we know that the gravitational potential initial is equal to the kinetic energy final. The amount of energy stored in the ball or system here is equal to the kinetic energy right before it hits the ground. That's what we mean by conservation of energy. Now, when it hits the ground is going to do some things that are going to cause it to lose some energy. During that process of hitting the ground, we hear some sound, right? Sound is carried by sound waves, which carry energy. And so some energy is being carried away as the sound. Some of the energy goes into compressing and then allowing the ball to decompress, which not all the energy is saved there. Some of it is lost in the process of those molecules bending and shaping, rubbing against one another. There's some energy lost there. And so in this situation, the normal force, which is non-conservative, causes my ball to lose some energy. Okay? Once it leaves the ground, now the only force on it again is gravity, and energy will be conserved from the moment that it leaves the ground until it gets to its new height. However, I cannot conserve energy from the very beginning until the end because there's a piece in there where there is a non-conservative force, that force of the ground. Normal forces, friction, those are non-conservative forces. Anytime those are available, they're going to cause a loss or a gain of energy unless, and we talked about this in class, unless they're perpendicular. If those forces are perpendicular to the motion, then they'll cause a change in the direction. Remember, we were just looking at centripetal forces, and a centripetal force causes your object to change its direction without changing its speed, without changing its energy. So perpendicular forces, please remember, and there's a spot for this in your notes, perpendicular forces do not cause a change in energy. You can still conserve energy if you have forces that are always perpendicular. All right? So, just in summary, we have this idea that as long as our forces are conservative and internal, then we should be able to conserve energy. If forces are external, then we should have some kind of change in the energy. The speed with which you hit the ground is not the same as the speed with which you leave the ground. And yet at the ground, the gravitational potential energy is 0 before you hit the ground and after you hit the ground. It stays 0. So the only thing changing there is our kinetic energies. Because the kinetic energies are changing, these are different, it means that the ground must be doing some work. It must be either putting energy in or taking energy out. And I think we can tell that as we drop the ball, because it doesn't go as high as it did before, the ground must have taken some energy out of our system as the ball hit it. Okay? Now, I have another example that I'd like for you to look at just to kind of try to put these ideas together again. And this is one that you've seen before. It's the pendulum. And we may have done this in class, but just to kind of remind you of how this works and the idea of conservation of energy, if we start with the pendulum right here up next to my face, and then I release it, I can stand here without any concern of it swinging back to hit me in the face. So remember, the idea of a pendulum. What are the forces? Let's get rid of what we had here. Think about this. When my pendulum is at its maximum height, okay, and I release it, okay, it starts swinging in this arc, and then it swings back along the arc. All right, so let's see if we can draw that, and let's show. So it starts here. It connects to the ceiling. It swings down, at which point it's at its lowest point, and then it swings back up. How high does it go? Well, it should go to the same height that it started at. Okay, so this is 3 different positions of the pendulum. Now, let's look at the forces on the pendulum at each of those points. Okay? So, at this point, the pendulum starts moving down this way. What forces are on it? Well, you've got the force of gravity that's pulling down. Should go back to this one. So we'll go force of gravity, which is down. You have the tension, which is up that way. And assuming no air resistance, there are no other forces. Now, as you start to decide, well, is energy conserved? One of the things you should look at is this. Force of gravity. If we talk about the pendulum Earth system, gravity is internal, and it's a conservative force, right? It's included in our gravitational potential energy there. If we look at the tension compared to the motion. You see how that's a right angle? The tension is perpendicular to the motion. And this is actually true no matter where we are along the path. At this point right here, as it starts to swing, now it's moving in this direction, but here's the tension, and look at that. It's still perpendicular. No matter where we are along the path of the pendulum, the tension in the string is always perpendicular to the actual motion of the pendulum. Now, what that means is that it doesn't do work. It doesn't add in energy. It doesn't take out energy. Therefore, energy of the pendulum can be conserved. The only other force is the force of gravity, which we've already talked about, is a conservative force. And so, therefore, in the situation of the pendulum, energy is always conserved. All right? Now, any situation that we look at, we get the same thing. Now tension is this way, but the motion is to the right. That's perpendicular. And of course, we do have the force of gravity down. And so what we can see in a pendulum or anything that's swinging like a pendulum is that the energy will always be conserved. All right? What does that mean? Well, that means if we make this some height, easiest way to do it is to make this height 0. And so however high that is, right, that's going to be my maximum height. So whatever height it has there, it's going to have gravitational potential energy. As it swings down, it starts to lose that gravitational potential energy, and that gravitational potential energy starts to turn into kinetic energy. Now, it depends on what point I'm interested in. If I want to know something about the bottom point, then I'll make this my initial, that my final. And then you should be able to find out that as the gravitational potential decreases, the kinetic energy will increase. You get faster and faster. At the bottom, you have your minimum gravitational potential energy, because that's my lowest height, and we have our maximum kinetic energy. If you think about it in terms of the blocks, remember last semester I showed you the blocks. There's a certain number of blocks, certain amount of energy, and as the height goes down, the gravitational potential energy is getting turned into kinetic energy. Those blocks are all being shifted over until they've all been shifted over to kinetic energy. Now, once it gets to the bottom, then it starts going up again. So as it goes up, that kinetic energy is turning back into gravitational potential energy. But no matter what happens here, I start with a certain amount of energy, a certain number of blocks, and so therefore when it gets back up to the far end, it's going to have the same amount of energy that it started with. It's going to have the same number of blocks. And if all of that is gravitational potential, then it's going to go up to exactly the same height that it had on the other side. That's why it's safe for me when I swing the pendulum to know that it's not going to come up and hit my face, because it's always going to go up, back up to the same height that it started from. Now, realistically, there's a little bit of air resistance, which means air resistance always opposing the motion is a non-conservative force, which means that it's actually losing some energy. So by the time it swings over and comes back, it's actually going to have a little bit less energy than what it started with, and so it's not going to go as high as it did before. Now, you can kind of picture this as being like a roller coaster. We're going to start looking at roller coasters next class, and a roller coaster will start at a certain height, and as it goes down a hill or as it drops, that gravitational potential energy turns into kinetic energy. The total energy still has to stay the same, but it can be changed back and forth between those two. As it gets down to its lowest height, if it starts to go back up again, then that kinetic energy will go right back into gravitational potential energy. If there's no friction, that's it. We don't have to worry about anything else. If there is friction, friction is then going to do work, just like the air resistance as my pendulum swung over and back. And so if there is friction, then there will be some energy loss, and our final height will never be as high as our initial. Okay? So I hope that that's helpful for some that are still struggling a little bit with the idea of energy. And we will continue talking about this, working with it as we start to look into some roller coasters and other drop rides in class next time. Okay? See you then.